So we saw in the last couple of videos that there are various difficulties with induction and confirmation. Today we're going to examine Karl Popper's views. Generally, scientists themselves don't really pay much attention to philosophers of science, but Karl Popper and his theory of falsificationism is very highly regarded and quite often mentioned by working scientists. So that would suggest that Popper hit on something important. On the other hand, I also think that the scientists who admire Popper have probably underestimated just how radical his views actually were. Popper claims to solve the problems posed by induction and confirmation, not by showing that induction can be justified, but rather by showing that science doesn't actually need induction at all. So Popper solves the problem of induction by eliminating induction. He thinks that the skeptical arguments against induction are conclusive. So Popper thinks that induction cannot be justified. I should say, as a historical note, he did a lot of his writing before Nelson Goodman presented the new riddle of induction with all the Green and Grew stuff. So Popper's theory was inspired initially solely by Hume, but obviously somebody who is skeptical of induction could appeal to Goodman's new riddle as well. So that's why I put it before in the series. Popper's theory is sometimes called deductivism because he thinks the logic of science is entirely deductive. It's science without induction. And we'll see how this works shortly. So first of all, Popper was not just concerned with the problem of induction. He originally set out to answer what might seem to be a somewhat unrelated problem, the demarcation problem. This is the question of how to distinguish science from pseudoscience and other forms of non-science. What is it exactly that makes something science? What is it that makes a theory scientific? What is it that makes a person have a scientific attitude? Most people tend to assume that this has something to do with the method, right? Science involves a special method for evaluating claims, and this was also Popper's view. So what is it? What is this special method that science uses? Well, Popper began his career in the early 1900s, and at the time there were a lot of radical new ideas going around in academia. In physics, he was particularly impressed by Einstein's theory of relativity. In other fields, we have Marxism in economics and Sigmund Freud's psychoanalysis in psychology. The precise details of these theories isn't really important, but I'll just briefly review them. So Marxism is an economic theory. It was adopted by the Soviet Union and by many other countries over the 20th century. And it views the historical development of societies as being driven by class conflict. So there are different socio-economic classes. You have the labourers or the proletariat, which is most of the population. They do the work. They work in the factories and so on. And then there are the bourgeoisie, who are the private owners who own the factories and other industries and who profit from the labour of the majority. Marxism proposed that social unrest between these classes will lead to revolution, which will eventually give way to a new social system of communism, where there are no social classes, where there is no state, where everybody has common ownership of the means of production. Marxism was quite a complex theory. Again, that's extremely brief summing up. I'm certainly no expert on it, so don't really take my word for any of that. Anyway, that's my understanding of it very briefly. Psychoanalysis was proposed by Sigmund Freud, and this sort of combines psychological theory with various psychiatric techniques for dealing with mental problems. It popularised the notion of an unconscious mind. Freud thought that people were driven by unconscious desires and beliefs, which are often irrational and which are influenced by events in your early childhood. Traumatic experiences as a child create, unconscious drives that influence your behaviour over your whole life. And you may not remember these traumatic experiences as an adult, or you may not realise their significance. And this is because the mind can repress memories that it finds too difficult to cope with. Most mental illnesses, according to Freud, result from the conflict between the unconscious and the conscious mind. Anyway, Popper felt that these theories, though perhaps interesting, were not properly scientific. Einstein's theory had some special feature that these theories lacked. So the question is, well, what is it that's wrong with Marxism and psychoanalysis? Now, initially, right, we might think, well, the trouble must be that they haven't got enough evidence in favour of them. Certainly if you adopt naive inductivism or the hypothetico-deductive method, then the point of science is to kind of gather evidence. But Popper says actually these theories were very well supported by the evidence. The average Marxist could find numerous confirmations of the theory just by opening up a newspaper. Almost everything that was happening in the world could be explained in terms of Marxism. You could explain almost every sort of social event in terms of class conflict. And no matter what happened, no matter how societies developed, even if it contradicted Marx's original predictions, well, the Marxists were able to form an explanation. I mean, obviously there was no social revolution that led to a communist utopia. I believe actually Marx predicted that there would be a social revolution first in Germany, which did not happen. And obviously, as I say, over the 20th century, there was no communist utopia. That didn't happen. And yet Marxism persisted for many decades because they were able to explain away these difficulties. Similarly, almost any human behaviour could be explained in terms of psychoanalysis. Popper gives the example of two behaviours. A first man pushes a child into the water, trying to drown it. The second man risks his life attempting to save the drowning child. Popper says that Freud can explain the first behaviour in terms of repression and the psychological conflicts resulting from that, whereas the second behaviour can be explained as sublimation, which is a state where socially unacceptable impulses are transformed into socially acceptable behaviours. Any conceivable behaviour, according to Popper, can be explained by psychoanalysis. Anything, any conceivable behaviour. So it's so we saw in the first couple of videos, as I say, that many analyses of the scientific method emphasise confirmation. But confirmation is easy. Any theory can gather confirming instances. It's not difficult to find evidence in the world which seems to support your theory. So in a certain sense, the problem with Marxism and psychoanalysis is that they actually have too many confirmations. They are compatible with every conceivable occurrence. They can explain any conceivable observation. They're basically confirmed by everything. They are irrefutable. But irrefutability is not a good thing. If a theory is irrefutable, that means that there is no way to genuinely test it. A genuine test of a theory requires that, at least in principle, the theory must be able to fail the test. And so the trouble with Marxism and psychoanalysis is that there were no tests they could fail, because anything that happened, right, for Marxism, anything that happened in the social realm could be explained in the Marxist terms. For psychoanalysis, any human behaviour could be explained in psychoanalytic terms. So there was no way of setting up a test that in principle they could fail. Now, we can then contrast this with Einstein's theory of general relativity. For Popper, what's so striking about this theory is that it takes serious risks, because Einstein makes very specific predictions. For instance, Einstein predicts that a large mass will bend light about twice as much as was predicted by the Newtonian theory. Now, we can confirm this by taking photos of the sun during an eclipse. In an eclipse, the sun is blocked out, so we can see the apparent position of the stars behind the sun. Einstein's theory predicts that due to the bending of light, they will be somewhat off the point that they would be observed at were the sun not there. So you can see how this works in this diagram from the University of Oregon, I think. Here's the actual star, and you can see that the light is deflected by the mass of the sun. So when we observe the star from Earth, it appears to be at a different position than we would see it were the sun not there. So as I say, Einstein's theory specifies a certain observational consequence. He predicts gravitational light bending, and this can be checked by observations, and if we observe this, it confirms the theory. But the point isn't the confirmation. The point is that if you were to observe something else, right, if you were to take the photo of the sun during the eclipse and you weren't to observe the apparent position of the star shifting, the theory would be refuted. Right, so Einstein's theory, it's not compatible with everything. It rules out certain observations. Right, if you photograph the sun during the eclipse and then you find that the stars are in their normal positions, the theory must be rejected. So whereas inductive support can be found for any theory whatsoever, what properly scientific theories do is they specify circumstances under which they would be shown to be false. So we know how to falsify Einstein's theory. Okay, you go to the sun during an eclipse, you look at the apparent positions of the stars, and if the stars are not where Einstein predicts them to be, his theory is wrong, and that's it, and we have to throw it out and start again with something else. And that's very different, Popper says, from the Marxist and the psychoanalyst. Now, there's an interesting asymmetry in universal generalizations. So consider statements like all metals expand when heated, or information travels from DNA to RNA to protein, never from protein to DNA. This is the so-called central dogma of molecular biology. Now, we can never prove that universal generalizations like these are true. No matter how many examples we find of a metal expanding when heated, it's always possible that the next metal might fail to expand. No matter how many times we sort of look at the information travelling in biological processes, we always might come across a case where information does travel from protein to DNA. And that's the basis of Hume's argument against induction, as we saw. But these statements can be proven to be false, because just one instance of a metal failing to expand when heated falsifies the hypothesis that all metals expand when heated. Just one instance of information flow from protein to DNA would falsify this central dogma. We can never prove this to be prove. Obviously, that should say we can never prove this to be true. Bit of a typo there. So we can see then that as I say, we can't prove any of these universal statements to be true, but what we can do is we can show that they're false. We can falsify them. And this is what Popper builds into his theory of science. So according to Popper then, there are two stages of science. First of all, you make a conjecture, a hypothesis that explains some phenomenon. Now, ideally, this conjecture should be as bold as possible, which is to say, it should make various risky predictions. A risky prediction is a prediction of an observation that is, a priori unlikely. It's an observation we wouldn't expect, that we would find unlikely given our previous knowledge. Einstein's prediction of the gravitational deflection of light was very risky. Given the theories that were accepted before Einstein, his estimate for the degree of gravitational deflection of light was not a phenomenon that you would expect to see. So that places the theory under a lot of risk. Einstein is making a prediction that is a priori unlikely. Stage 2 is the attempted refutation. You test the prediction. If your observations contradict the prediction, you throw out the hypothesis and make a new one. If your observations match the prediction, you go back, derive another prediction, and continue until the hypothesis is refuted. And then when the hypothesis is refuted, you can go back to stage one and make a new hypothesis. And that's how science develops. Bold hypotheses followed by attempted refutations. Even a hypothesis that survives 1,000 attempted refutations might be eliminated by the next test. So, according to Popper, the problem of demarcation is solved. What distinguishes science from non-science, or pseudoscience, is falsifiability. Scientific theories make predictions such that if the prediction fails, the theory is refuted. Now, one thing that may be worth mentioning is that Popper does not say that there's anything necessarily wrong with unfalsifiable theories. He says only that they are not scientific. So he's not necessarily making a normative judgment here. He's just trying to delimit the boundaries of science. Psychoanalysis and Marxism may well be good theories. They might be useful and fruitful ways of thinking about the world, and perhaps they will inspire the development of scientific theories in the future. But they are not themselves scientific. So that's all Popper's saying. He's just trying to find a way to distinguish the things that are science from the things that aren't. And falsifiability is his criterion there. Now this also shows us why the problem of induction can be dismissed. There is no induction in science. The method is purely deductive. Specifically, it's an application of a deductive rule called modus tollens. Modus tollens is a deductive argument of the form: if x, then y, not y, therefore not x. The truth of these premises guarantees the truth of the conclusion. So, if Socrates is a man, then Socrates is mortal. Socrates is not mortal, so Socrates is not a man. We can, if you have those two premises, that if Socrates is a man, then Socrates is mortal, and the premise that Socrates is not mortal, then it's guaranteed to be true that Socrates is not a man. It must be the case that Socrates is not a man, just logically, right? So this is a deductive argument. So how does this work in the case of science? Well, the application to science will look something like this. We'll be saying, well, if general relativity, then gravitational light bending, right? So if general relativity is true, then we will observe, the gravitational deflection of light. I mean, of course, you don't observe exactly the gravitational deflection of light, but you would observe the changes in the apparent positions of the stars. So anyway, if general relativity, then gravitational light bending. So if we fail to make the observations of gravitational light bending, then we can deductively show that general relativity is false and has to be thrown out. Failure to make the observations predicted by general relativity deductively refutes the theory. There is no induction here. Now, this procedure that I've explained might seem similar to the hypothetico-deductive method, and broadly speaking, falsificationism does adopt this method. But there are two important differences, at least based on how I explained the hypothetico-deductive method in that second video. First of all, the hypothetico-deductive method allows scientists to come up with hypotheses however they like. They can come up with whatever hypothesis they want. Now, Popper makes the constraint that hypotheses must be bold. They must make risky predictions. So scientists shouldn't propose just any hypothesis. They need to focus on the risky ones. They need to focus on hypotheses that can be refuted if we make the right observations. So, hypotheses which specify many ways of refuting them are bold hypotheses. The bolder a hypothesis is, the more ways you can test it and potentially refute it, the more scientific it is. Einstein's theory of relativity made numerous surprising predictions, so it was an especially bold hypothesis. So what Popper says is, we have to invent hypotheses with a view to increasing boldness. Second, and I think perhaps most importantly, according to falsificationism, confirmed predictions of a hypothesis are not taken to confirm or support the hypothesis. So no matter how many correct predictions a hypothesis makes, we never establish that the hypothesis is probably true. The activity of science is focused entirely on the attempt to refute theories. All we can ever say of a scientific theory is that it has not yet been refuted. But of course, there will be an infinite number of theories that have not yet been refuted, right? So the fact that a theory hasn't been refuted gives us no reason whatsoever to believe that it's true. Okay, science never confirms theories. This is a consequence of Popper's rejection of induction, and it's, I think, probably the most radical aspect of his philosophy. So in lieu of confirmation, Popper introduces the notion of corroboration. So this is quite an important distinction. If you see Popper talking about confirmation and corroboration, it's important to keep this distinction in mind. Corroboration is a measure of how many tests a theory has passed and how risky those tests were. So the more tests a theory has passed and the riskier those tests were, the greater the corroboration that theory has. Einstein's general relativity has passed pretty much every test we can think of, and many of these tests were very risky. So we can say that it is highly corroborated. But it's crucial to realise that greater corroboration does not imply greater probability of truth. Yeah. So if we say that a theory is highly confirmed, right, we would be saying that it has a greater probability of being true. But that's not the case with corroboration, right? Corroboration is just a measure of sort of how well the theory has performed in the past. How many tests it has passed and how risky those tests were. But no matter how many surprising, risky predictions a theory gets right, we should never believe the theory is true or probably true. We should not believe even that it's more likely to be true than it was before the test, right? So passing a test does not even raise the probability that a theory is true. I think it's worth distinguishing this from a weaker thesis, which we might call fallibilism. Fallibilism says that we can never be certain that a theory is true. So certainty is not attainable, but we might still believe the theory. We might have the attitude, since general relativity has passed so many risky tests, it's likely to be true. It's somewhat likely to be true. Presumably, I think no scientist or philosopher of science would say that we can be certain that general relativity is true. It's obviously possible that it might be refuted. So the fallibilist says, you have to be open-minded, you have to recognise that you might be wrong, but you can still make judgments about whether something is likely or more probable or whatever. So just to illustrate this with an everyday example, we might say, look, I can't be certain that I'm that there's a computer in front of me right now. It's logically possible that I'm just hallucinating this. I can't be certain that I'm making this video. I could just be hallucinating. Similarly, you can't be certain that you're watching this video right now. You could be hallucinating. Even the most seemingly obvious propositions, it's logically possible that they could be wrong. But of course, I still believe that there's a computer in front of me, and presumably you still believe that you are indeed watching a video on philosophy of science. Similarly, I believe that my car is parked outside. I'm not quite so confident of that. After all, maybe it was just stolen. But I'm pretty sure that if I go outside right now, I'll see my car. So we all have various beliefs that we hold with various degrees of confidence. And we might hope that scientific research produces theories and allows us to increase our confidence in some of these theories. But Popper's claim is much stronger than fallibilism. For Popper, passing a test provides no support whatsoever for a theory. We should not be more confident in the truth of general relativity than we were before its predictions were confirmed. So, I'm hammering this point home because I think a lot of people don't really appreciate how radical Popper's position here in this case is. In particular, I think when scientists praise Karl Popper, I think they've probably missed this aspect of his position. They like the emphasis that Popper puts on testing and falsification. All theories are potentially falsifiable. All theories should make risky predictions. All theories should be subjected to severe testing and all of this. Yes, that's all very good. But I think the further claim that there is no such thing as confirmation, that we can never have any confidence at all in the truth of our theories, that's something that I think many scientists would actually find quite unsettling. So that is, basically speaking, Popper's view of the scientific method. Now, there is something of a snag in Popper's method which needs to be noted here. This is the problem of ad hoc hypotheses. So we pointed out in the video on the hypothetico-deductive method that theories in themselves don't entail any predictions. In order to make predictions, theories have to be supplemented with auxiliary assumptions and with assumptions about initial conditions. But this means that if the prediction doesn't turn out as we expect, we can always suppose that the problem was with the auxiliary assumptions rather than with the theory. So we saw the example of Boyle's law. Boyle's law predicts that if you have a gas at a constant temperature, then if you halve the volume of the gas, the pressure will double. Let's say we do the experiment, we halve the volume, but we find the pressure doesn't double. So has this refuted Boyle's law? Well, really, no, right? I mean, we would probably suppose, okay, maybe there was some sort of failure in the equipment. Maybe the pressure gauge isn't working properly, or maybe the temperature wasn't kept constant, or something else. You wouldn't just throw out Boyle's law just on the basis of an experiment that goes a bit wrong. And in fact, I mean, if you think back to physics or biology classes in high school, it just occurs to me, high school is an American term, isn't it? It's secondary school. I am in England. I should say secondary. Is it second? I don't even know. It doesn't matter what it is. Sorry. I went off on a little bit of a tangent there. So anyway, think back to the experiments that you would have done in biology, say in secondary school. A lot of them just didn't work, right? I don't know, maybe you tried to cultivate some bacteria or something on a petri dish, but it just didn't work, right? It failed. What you don't then think, okay, I've refuted this accepted biological theory. Instead, it's simply that no, there was some sort of problem with the equipment. You didn't set up the experiment properly, something like that. So the worry that arises for Popper then is, well, it looks like theories can always be saved from refutation by kind of just making ad hoc hypotheses, right? By just introducing hypotheses that explain away the failure of the prediction. After the discovery of Uranus, it was found that the orbit of Uranus diverged from the predictions of Newtonian mechanics. So did that mean that Newtonian mechanics was refuted? No. Indeed, it would have been crazy to throw out a remarkably powerful and comprehensive theory just because the orbit of a particular planet didn't fit. Instead, it was proposed that the discrepancies in Uranus's orbit were due to the gravitational influence from an eighth as yet unobserved planet. And the position of this new planet was worked out by Urbain Le Verrier, and very shortly afterwards was confirmed. And this was taken to be a triumph of the Newtonian theory, and I think it's it's kind of understandable. When you look at what Le Verrier did, is he analysed the discrepancies in Uranus's orbit, and he used those discrepancies in order to plot exactly where where Neptune, the eighth planet, should be. And very shortly after he made that prediction, it was confirmed exactly where he predicted it. Now this seems perfectly scientific. But the proposal of a new planet was made simply to save the Newtonian theory from potential refutation. It was an ad hoc hypothesis. It was a hypothesis introduced simply to save a theory from falsification. So what can Popper say about this kind of case? Well, bear in mind that for Popper, scientific status is something that comes in degrees, right? So a theory that is very bold and that takes many risks is more scientific than one that takes fewer risks. Similarly, Popper says, okay, scientists, it's okay to appeal to ad hoc hypotheses to save their theories, right? But for each new ad hoc hypothesis that is proposed, the scientific status is chipped away. Scientific status is decreased somewhat. So when the proposal was made that maybe there's another planet beyond Uranus, that slightly decreased the scientific status of Newtonian mechanics. Now, if the prediction of Neptune had failed, and so some other ad hoc hypothesis was then proposed, that would have decreased the scientific status even further. And in fact, something similar, I think, did happen with Mercury. Mercury also exhibited certain discrepancies from the Newtonian prediction, and there was it was proposed that maybe there was a planet closer to the Sun that was influencing it, called Vulcan. But obviously, Vulcan was never observed because there is no Vulcan, and various excuses, I guess, various ad hoc hypotheses were proposed to explain this. It turned out that the reason why Mercury diverges from Newtonian mechanics, that was an effect of relativity. But in that example, the prediction of a planet closer to the Sun, it kept failing, and excuses kept being made, and so you can sort of see that the scientific status gradually gets chipped down. I mean, on the other hand, you can see that there might be a bit of a worry here for Popper, because when you read the case of Uranus and the prediction of Neptune, I mean, it doesn't seem as though the scientific status is decreased at all. In fact, it looks like Leverrier's work was really exemplary scientific work. So this may be a bit of a problem. I might talk about it a bit more in the next video. A final question before we end, which may be worth considering: is falsifiability a property of theories, or is it more an attitude of good scientists? So Popper usually talks as if falsifiability applies to theories. But the obvious problem with this is that it seems that any theory can be made falsifiable. I could adopt a theory of, say, astrology, and then make various predictions, and be sincerely willing to give up the theory if those predictions fail. I could say, right, okay, I predict that people who are born when Mars is at a certain position in the sky will tend to be better at physical activity than other people. That's my astrological prediction. And if the prediction fails, I will give up the theory. I won't try to save it by making ad hoc adjustments or anything like that. I'll give it up. So does that mean that we now have to count astrology as a science? That doesn't seem quite right. So the problem is that if falsifiability is a property of theories, well, it looks like, I mean, any theory can be made falsifiable or unfalsifiable. So we might then think, well, maybe falsifiability is more an attitude, right? It's an attitude that scientists should adopt. So it's not that astrology as a theory is scientific or unscientific. We need to look at the attitude of the practitioners. So sure, right? If you became an astrologer and you derived predictions and you were willing to give up the theory if those predictions failed, then you would be a perfectly good scientist. The problem with astrology is that the vast majority of astrologers don't have that attitude. The vast majority of astrologers do not make risky predictions. On the other hand, the vast majority of physicists and chemists and astronomers and biologists and so on do have the right attitude. When we look at astronomers or chemists or whatever, we find that they make risky predictions and they're willing to give up their theories. And so the difference between astrology and astronomy is in the attitude of the practitioners. But the problem with this is that actually many scientists are quite dogmatic. This is even true for Einstein himself, who Popper regarded as an exemplary scientist, as we have seen. Einstein wasn't actually too worried about potentially incorrect predictions. There's a famous quote when asked how he would have reacted had the observations of the eclipse contradicted the prediction of light deflection. Einstein responded, well, then I would feel sorry for the dear Lord. The theory is correct anyway. So it looks like he wouldn't have given up the theory even if the prediction had failed. And I think you can find the same when you look at biographies of scientists. Many of them seem to have actually quite almost close-minded, dogmatic sort of attitudes. So there's a question then about whether falsifiability is a property of theories, or is it maybe a sort of attitude, a way in which we should approach theories. Either way, we're starting to see some difficulties here. That's all for now. In the next video, I'll look in a bit more detail at some objections to Popper's theory. But as I say, that's it for now. Thanks for watching.